In this first video for sections 2.4 and 2.5, we're going to talk about higher order partials. Before I do that though, I want to just jump back and remind you of a few things. So this week in the video series, we're going to have 5 videos, but a couple notes here. We're only going to focus on on 2.4 through page 138, and the videos actually won't focus on the sum, difference, product, quotient rules. Really, they're the same as one dimension or one variable calculus, just now with multiple variables. And in 2.5 we're going to do it all, but really anything prior to theorem 5.3 is really just a result that will lead up to 5.3, so we're going to focus on that one when we get into that particular section. Alright, but to begin, we're going to talk about higher order partial derivatives. And so, well, the first question is, what can we do about them? And I have a function here. Okay, well, we could maybe, if it's differentiable, right, we can just keep on differentiating. So we could do that, right? So we can look at partials, but the general case when we have Rn to Rm, that one we don't quite know about, because again, that's where we got that derivative matrix going on. And right now we have just a function that has one output, and so we can deal with functions in that case, and that's kind of the lens which we're going to work under. Okay, so as we already know, we can find partial derivatives by doing del f del x, which, just a reminder, we can use f sub x in that, and that's the notation I'm going to proceed with just because it's going to be shorter here. If I do that, I get 6x plus 4y, okay, and similarly, if I do f sub y, that is going to be 4x minus 14y, okay, but now I can keep differentiating, right? I can do fx, alright, and then differentiate that again with respect to x, which notation-wise we're just going to call that f sub double x, okay, and all I get here is 6, okay, and I could do the same thing with y, so f sub y, alright, and well, that's just going to be minus 14. Okay, that's fun. But what if I do those in different orders? What if I do, say here, I do f sub x with respect to y, right? Well, don't I just get 4? Yeah, because I would take the derivative of f sub x now with respect to y, and notation-wise, I'm going to do that f sub xy. Similarly here, I could say, well, I'm going to take this, I'm going to say, alright, let's look at f sub y, and now differentiate that with respect to x. Notation-wise, that would be f sub yx, and this is just going to be 4. Alright, well that's kind of fun. It's also interesting that I got 4 in both of those cases. So I have f sub xy is equal to 4, which is equal to f sub yx. Okay, that's kind of interesting, and I'm thinking something might be going on here. And so here I just looked at the second order partial derivatives. You could continue and, do f triple x is just 0, and similarly f sub triple y is going to be 0. Okay, so you could continue on. Okay, and just for notation purposes, again, to remind you, when I say this, this notation here, that's a shorthand notation, but I'm really saying longhand notation, that f sub x with respect to x, that would be del x, of del f del x, and that would be del squared f, and then del x squared. Okay, and similarly for For y, it would just replace it. But if I have that mixed partial derivative, and I use the language of mixed partial derivative to indicate that I'm doing two derivatives, but they're not this with respect to the same variable. This would be del y of del f del x. Okay, or you can say this is del squared f and then del y del x. Okay, and so the order does really matter here. It indicates that you do the x derivative first of for the x function or the f function, and then the y derivative. Okay, so notation does matter here. Okay, and I say that a bit tongue-in-cheek because I'm going to ask this question: does the notation really matter? Well, mathematically speaking, of course. But at least in the case when we have mixed partial derivatives, we have an amazing theorem proven by a French mathematician called Clairaut. And so all this assumes is that we have some open domain. Okay, so we generally here we aren't going to worry about it too much. And then we have first and second order partial derivatives of f on that domain defined in an open ball, so they're just defined, and then we have to have them being continuous. Then all this says is that mixed partial derivatives are nice. So really, takeaways here is if f is quote-unquote nice, then we have f sub xy is equal to f sub yx. Okay, and this is going to get us through many, many hurdles. And this will be the end of the first video. We'll go on and talk about the geometry soon.